Hi, welcome to this video on correlation analysis. So let's load the necessary libraries. Here we are going to use the insurance data set in which every row belongs to a customer, and we have customer age, gender, their BMI, number of children, whether they are smoker or not, which region they belong to, and what is their medical expenses. So this one row represents one customer, and this is the granularity of the data. So now I want to understand the relationship between multiple numerical variables that are available here. Especially I want to know which are those columns that are related to my expenses. So this data actually can be used for regression analysis, in which your expense column will be your target column. So we would like to know, while building the model, what impacts the expenses, and especially in correlation analysis we will understand how other numerical variables like age, BMI impact expenses in a linear fashion. That is what correlation analysis will let you know. It will not give you non-linear relationship, it will give you only linear relationship. So let's see how we can analyze this data using correlation analysis. So first we will start with path plot. So what is a path plot? Path plot will give you a matrix like structure. For example, here it has identified four numerical variables in our data. One is age, BMI, children, and expenses. So these four numerical variables will be available in the columns as well as in the rows. So you are seeing here, first column is age, second column is BMI, third column is children and expenses. Likewise, you will also see the rows as well in the same format. So first row is age, second row is BMI, third row is children and expenses, like this. So the first row, first column is for age. So you're just trying to correlate age with age. So in which case it's just a histogram. So we will get to know how age is distributed. You can see it is almost uniformly distributed across multiple ages. Then comes your age versus BMI. So x-axis is age, y-axis is BMI. So we get to know how the relationship exists using a scatter plot. So here you can see it is completely scattered. So I can't really identify a relationship between age and BMI. Okay. Then again, age versus children. So not much. Children is mostly a categorical variable here, at least just because it is having some numbers, it is coming in path plot, so we can just ignore that plot. And finally, important one, age versus expenses. So how is age impacting expenses? So you can see there are three different groups, and in each group you can see as age increases, expenses also increases. But overall, if you look out, it might look scattered, but within the groups you can see they are linearly related. As age increases in this group, expenses also increases proportionately. So that is a kind of relationship within groups that we have, but overall it looks like a scattered one. Likewise, the second column, BMI, we can identify what is the relationship for BMI with expenses. So you can see again there is two set of groups, one group here and another group here. So somewhere around 28 or 29, there is a second set of group with higher expenses, as well as there is another group here which is having moderately lower expenses. So this group is having relatively higher BMI and higher expenses. So likewise, children, as we said, might not be looking at this case. It is mostly a categorical variable, or even if you consider it as a numerical variable, you can see children doesn't impact, number of children doesn't impact expenses, because people with zero children also have expenses ranging between lower value to higher value. Likewise, people with number of children 3 is also having a range between lower expenses to higher expenses. So children here, at least directly, it's not that correlating with expenses. So expenses with this expenses, so it will be a histogram. So you can see this is a right skewed distribution. So likewise, this matrix like structure will help you to understand relationship between various numerical columns in your data. So this is a visual representation, right? So this is always good to have a visual representation, because most of the analytical algorithms might not give you the exact result that you're looking for. So it's always best to have your visual analysis done, get a picture of your data, and then go for quantification. So here I'm going to use the data frame name dot corr for correlation. So I'm going to compute pairwise correlation. So for every numerical column, pairwise numerical column, we'll be computing correlation. For example, correlation between age and age is 1. Correlation between BMI and age is 0.1. Correlation between children and age is 0.04. Likewise, for every pair of numerical variables, we will have correlation value. The diagonal values will always be 1 in correlation metric. The values below the diagonal will always be same with the values above the diagonal. For example, the correlation between BMI and age is 0.109. Likewise, correlation between age and BMI is 0.109. So these two values will be same. This value and this value will be same. So the values in the lower diagonal as well as the values in the upper diagonal will match. So that is the property of correlation matrix. So this will be very helpful to quantify your inferences. Okay, so we can just use a simple gradient technique to color code your correlation metric. So I'm using panda style properties, and then within style we have various properties like highlighting or just coloring each row. So here I'm using background underscore gradient. So the cells will be colored based upon the values that they take. So here we can see because of the high value of ones in the diagonal cells alone will be in dark shades, on non-diagonal values will be in lighter colors. So what I've done is, just to make sure that I don't get this dark bands in the diagonal, because for all the correlation matrix the diagonal values will always be 1. So no point in visualizing that. Instead I want to highlight the other colors, right? So what I've done is, I've just created a simple function here where it just takes a data frame as an input, computes the correlation matrix for that particular data frame, and then goes to each column, meaning column name. So it just loops through each column name, and then in this correlation metric it just looks for locating. So it just locates the row with that column name and column with that column name. So here first it will go with age. So it will just go to row which has age and column which has age, which is this cell, and then manually changing that value to 0. Okay, so this, I'm not telling that correlation between age and age is 0. This is just for visual representation. Okay, so it's just going to convert all these ones to zeros temporarily. Likewise, second time the call value will be BMI. So it will look for the row with index BMI and column with name BMI, and this is the cell which has row index BMI and column name as BMI. I'm converting that to 0. So likewise, I'll go to all diagonal values, convert the value to 0, just for visual representation. Keep that in mind. So in the next line, I'm converting everything into absolute values. So here I'm just interested in the magnitude of correlation and not the direction of correlation, just for this visual representation. Okay, so keep in mind, always you have to visualize correlation matrix like this, just for ease of understanding how variables are correlated to each other. I'm making diagonal values to be 0 and plotting only the absolute values. I'm going to remove the negative values. So keep in mind, two changes we have done. One is converting all the diagonal values to be 0, and then converting all the values with absolute values. So This is just for ease of representation. So now you can see there are other cells now that are popping up. So we can see the highest correlation as of now is between age and expenses, which we saw here as well, right? As age increases, expenses also increases. But then the correlation number should be higher, right? Obviously, zero point 0.3 is kind of weak correlation. Why is that happening? We discussed that earlier. Within groups there are correlation, but then overall if I look at age versus expenses, I don't see much of correlation. Values are scattered here and there. So what I'm going to do is introduce a categorical column in my path plot. So here I'm using hue equal to smoker. So my visual will be now color coded based upon smoker column. So smokers are represented using blue and non-smokers are represented using orange color here. That is the legend that we see here. So let's move on to the last row, which is important to us. So here we can see there are three set of groups color coded based upon whether they are smoker or not. So the first group in the bottom, now it just mix of oranges. We don't see any blue dots here, which means that all these people are non-smokers. And for non-smokers, as age increases, expenses increases, but not at a higher rate. Whereas this group is completely blue for smokers. For smokers, as age increases, the expenses increases in a very high value. So you can see the complete group is for smokers, whereas here it has mix of smokers and non-smokers. So lower values for non-smokers, very higher value for smokers. So clearly indicates that smokers column is a very important column. Likewise here you can see this group that we were discussing about, which was having high BMI as well as high expenses for smokers. So smokers whose BMI is above 28 or so, and their expenses is quite high. Likewise the expenses histogram now will be converted into kind of density plot where the orange curve is for non-smokers and blue curve is for smokers. So you can see non-smokers expenses are in the lesser side, less than 25,000, whereas smokers the value goes higher. So clearly you can see there is a difference between smoker and non-smoker. Okay. So this gives a better picture now. So we have a categorical column which is influencing our target expenses column. We will see how we can convert this binary categorical column into a numerical column. This applies only for binary categorical columns, especially yes or no categories. So what I've done is I've taken the smoker column and converting a new column in which if the value of the smoker column is S, I'm going to replace it with 1, and if the value of smoker column is 0, I'm going to introduce 0. So creating a new column is underscore smoker. 1 means smoker, 0 means non-smoker. So just to have it as a numerical column so that I can just use my correlation matrix to visualize that. So now you can see there is a huge relationship between smoker as well as expense. The correlation is almost 0.8. So this was not coming out with numerical columns alone earlier, right? The highest correlation was close to 0.3, whereas now we have highest correlation close to 0.8. So again I'm stressing this can be done only for binary categorical columns. We can convert them into a numerical column. Likewise what I've done is checking whether BMI value is greater than 28 or not. Likewise BMI smoker, so I'm going to multiply is BMI column here and is smoker column here, so that if a person is both having a high value in BMI and then he or she is also a smoker, so in which case we will able to get this particular group completely out. So for this group alone the values will be 1, rest of the groups the value will be 0 approximately, I'm mentioning. So we're just trying to target this group, so BMI with value greater than 28 and they are smokers as well. So this new columns I'm creating now, visualizing the correlation metric. So we can see here that BMI and smoker column has a huge correlation with my expenses column. So likewise I'm going to multiply my age and is smoker column also. So we can just see that we have age smoker and is smoker has a huge correlation again. So here we are just trying to bring in a categorical column and then converting that into a numerical column to do correlation analysis. So this gives a better picture of how your target variable is related to all the other input variables, how they are linearly correlated, and within the input variables how they are linearly correlated. That also you can check it out. So this is one of the pre-processing or one of the prerequisite step when you do machine learning model, especially regression analysis.